Yes, welcome back once again in our weak formulation. In the last class, we have discussed Neumann problem, with the Neumann condition with the first order term, and it was easy to get the existence, uniqueness and regularity. It was fine. Now we go to, there is a slight difference when you go to without a first order term. So, we will be working with minus Laplacian u equal to f in omega with du by d nu equal to 0 on d omega. So, let us issue. So, in general, so observations or facts, observations of facts. So, let me call it this to be 1 again. If u is a solution, then u plus c is also a solution for all constants for all c in R. So, that means there is no uniqueness, even if there is a uniqueness. This is the first thing. Okay. So, the first question you address, does this give all the solutions if there is a, does there exist any other solution? Does there exist any other solution? Luckily, no. So, if you can find one solution, no. So, if you can find one solution, then all solutions are given by u plus c. How does that prove? So, to see this, for if u1 and u2 are solutions of 1, then u equal to u1 minus u2 satisfies Laplacian of u equal to 0, can put a minus, and du by d nu equal to 0. Okay. That you get immediately. Now, multiply by u, integrate by parts, use the boundary condition. This is in omega, this is on d omega. Okay. Integrate by parts, multiply by u, probably you can take u from h1 of omega. Okay. Multiply parts gives you integral of grade u square equal to 0. The boundary term do not come. That implies u equal to constant. That is, any two solutions differ by a constant. Any two solutions, if x is differ by a constant. That is a one fact to observe. Okay. That is a one important thing first. So, you cannot look for solutions in h1 of omega, therefore, a suitable space would be, we will come back more to it, suitable space would be, the quotient space would be, we have discussed this, h1 of omega to R. Okay. Because you have already seen earlier, we have discussed this about the m plus 1 p omega, quotient it out by pm of omega, and you have seen that Poincare type inequality means the highest derivative can be estimated below from the highest derivative norm. The semi norm type can be estimated from this. So, there is a Poincare type between. So, this is exactly when m equal to 1 0, this is nothing but np equal to 2, this is nothing but your h1 of omega or r. Okay. So, we will come back to this one. So, before coming back to that, this immediately tells you the suitable space would be that one. So, you have to look for not one solution, you have to look for u and its constants, that is what I say. The second point I want to think about this is about the uniqueness regarding existence. Look at the equation, look at this equation and integrate. We get, if you integrate, you get integral over f over omega. So, f is, I start with f in L2 of omega, otherwise you have to do duality. So, that will be your minus Laplacian u over omega. Integrate by parts and you get integral over du by d nu over d omega. Okay. Maybe go to put a minus sign there. Okay. And then du by d nu equal to 0. So, this will be 0. Okay. All right. So, you see maybe plus I think, just check it. So, that implies integral of f equal to 0 over omega is a necessary condition. Necessary condition. In other words, if this not necessary condition, this is always important. If necessary conditions are not satisfied, if integral of f not equal to 0 over omega, no solution. So, you have to put, so you have to study the equation. So, we have to study, need to study this equation with study one with this is called compatibility condition, because it is a necessary condition, you have to impose it. Compatibility condition integral of f equal to 0. You see, that means basically you have to, of course, you may put conditions on u to fix this constant, that is a different thing. So, these 2 points immediately motivates you to look for solutions. So, look for solutions in h1 of omega. I will little bit again elaborate, though we have discussed in the general case of Wm plus 1 p of omega, but we will do with the fact integral of f equal to 0. That is what. Now, can we prove existence and uniqueness in this space? This space uniqueness is equivalent to saying the solutions are defined up to an additive constant. So, how do you define this space? On this space, this is done again, I am repeating once more. You define an equivalence relation that u equivalent to v if u minus v is a constant, see, constant. So, that gives you elements of equivalence classes, this is an element x. So, any 2 elements in the class is differ by a constant, and you also defined a norm on this. So, the idea is that you look for the smallest, nearly the smallest infimum, the smallest possible. So, choose the constant so that u plus c in h1 of omega for all c in R. This is how you are done Wm plus 1, you have added the polynomials of degree less than or equal to m, because here it is 0. So, you are proving this one, and this is the norm, and you know that this norm satisfies Poincare type inequality, satisfies Poincare type inequality. That is what we have done. That is what the general result. It's a and the special thing in this case is nothing but your Poincare-Oettinger inequality. That is all you are using it, Poincare inequality in this space. So, that is what this is the norm in this space, and you are defined that. So, you have this norm defined there. So, now you can form a weak formulation on X. How do you define a weak formulation? You define on X A from X cross X to R, you define A U V, you pick any element, does not matter, it is well defined. A U V is equal to integral of grade U grade V, because whatever be the element you pick from the equivalence class U, the grade of that equivalence class is the same, because so this is nothing but what I am saying is that grade of U, grade of V, this is what I am defining, and this is by definition, and by definition this is well defined, because whichever point you to choose from the equivalence class, it does not matter, because it is only differ, you are adding a constant and the grade of the constant is equal to 0. So, and you also define a linear form, this is the bilinear form, you define a linear form A integral of f v is equal to integral of f v, you choose any element, does not matter, because well defined. Here is the fact you are using, if I choose v equal to v plus c, integral of v is equal to integral of v plus c, but c is a constant and integral of f is equal to 0. So, it is also well defined integral of f. So, you are using this compatibility condition. Okay. So, you are bilinear. So, the one the form is 2. Now, your form is AUV is equal to integral of FV. Okay. This is for all V in X, and now apply Lax-Milgram. I am going to give another proof for you using, because that is another way of looking at it. Lax-Milgram implies there exists unique U, okay, in X. That is the way you can prove that. Okay. Yeah, so you have your existence uniqueness in that way, but there is, let me tell you another way, existence uniqueness, solution existence uniqueness, via Fredholm alternating, via Fredholm alternating. It is nice to learn these things. Okay. So, let me call these are the equation minus Laplacian of u equal to f in omega, u equal to 0, du by d nu equal to 0 on d omega, and integral of f equal to 0, okay, over omega. So, you get as is seen earlier, you get not just one unique solution, you get solutions and all its additive constants. You can fix the constant by demanding a condition like integral of u equal to 0, something like that. You can do that. And the technique of Fredholm alternative you are already seen. So, what I am going to do is a similar thing. So, how powerful this Fredholm alternative to the thing. Okay. Consider this is for lambda positive, you consider minus Laplacian of u plus the moment you add a 0th order term, then it is not a problem, f in omega, and there exists a unique solution, you already seen it, okay, and you do not need a condition right now, okay. So there exists a unique solution, so there exists unique u in h1 of omega, okay. So that is not a problem. So you have a solution map, exactly we have done it in the previous situation. You have a map G, so you have a map starting with L2, your f is in L2 of omega. You are starting with a map from L2 to H1, omega bounded, case you are getting omega, you are assuming smooth, all that. So you have a solution f going to u, that is a solution. So gf equal to u equal to gf, and this is compactly contained in L2 of omega, and that is identity map going to u gf, okay, identity map, and this map is compact, okay, compact. And what is the meaning? That is minus Laplacian of gf plus lambda gf is equal to f, okay. So you have that one. Again, as we have seen earlier, this is equivalent to u equal to exactly what we have g of f plus lambda u, okay, and you put again v equal to f plus lambda u, and this will become equivalent to let me write 1 over lambda v minus f is equal to gv, okay. So that is what we are getting, or v minus lambda gv is equal to f. So you have that exactly that identity, right? This is identity minus lambda g of v. So again, if lambda inverse, if 1 over lambda is not an eigenvalue, absolutely no difference. The difference is just coming now. Is not an eigenvalue, then unique solution exists, right? But you know that there is no uniqueness. So what does that imply? No, then unique solution exists, okay. So for every lambda positive, it is not an eigenvalue, you have a unique solution. So since we have already seen that uniqueness is not there, every lambda inverse is a eigenvalue. So the claim, okay, for lambda greater than 0, this is trivial, lambda minus 1 is an eigenvalue of G. Immediately you can see that it is not an exercise, but I would like you to realize yourself immediately. Any constant you take any constant is an eigenvector. Any constant, you can choose the constant here, okay. Constant at not any constant. You take f equal to g, constants are eigenvectors, okay. That means there exists f not equal to 0. In fact, what I am saying that is a constant. You can see that. I can write down, but I would like you to see such that gf equal to lambda inverse f. That is not difficult, right? Lambda inverse is a constant, and then you can see that gf is the solution. So if you take f is a constant, you know all that. So constant is the one you will be playing it. So every lambda inverse is an eigenvalue. So what you have to do? The thing is that, so and what we have seen basically the dimension of kernel of I minus lambda g is actually 1. That also you can say if you want to prove a proof of this. So, this is a claim that this is one dimensional space. Okay. And how do you see that one? If V is in the kernel I minus lambda g, that immediately tells you GV is equal to lambda inverse of V. Okay. But what does that mean, lambda inverse of V? This actually implies that Laplace minus Laplacian of V equal to 0 in omega. You can check that if you are not convinced, dV by d nu equal to 0, okay, on d omega. Because GV is this one, but what is GV? GV is a solution to this one. Okay. So, that means you will get immediately these two conditions, okay, plus conditions are there. So, that this will imply V is a constant, that we have already seen. So, only that. So, that means kernel of I minus lambda g you can identify with the reals because it is all constants. Okay. So, you got that. So, by now Fredholm alternative. What is Fredholm alternative will tell you? Fredholm implies 1 has a solution. So, what is 1? This is 1. 1 is not written here. Yeah. So, I can call this 1. 1 has a solution if and only if f is in the kernel of I minus lambda g. Here g is a symmetric operator. So, you do not have to take g star. That is equivalent to saying, because kernel of I minus g is a constant, that is if and only if f1 or f1 any constant f1 equal to 0. That is equivalent to integral of f equal to 0. You see. So, you have that. So, even with the Fredholm alternative you get that condition and you can prove. So, you can solve the more generally. So, that is about in homogeneous boundary condition you can consider more generally consider non-homogeneous condition, homogeneous problem, like minus Laplacian of u equal to f in omega and du by d nu equal to g on d omega. And what is the boundary condition you need to take here? So, exactly you do this trace theorem, and what is the compatibility condition? Compatibility condition. Compatibility condition is integral of f is equal to minus integral of Laplacian of u over omega, and that by integration by parts you get minus du by d nu over g over boundary of omega, that is nothing but minus integral of g over boundary. So, that implies the compatibility condition is integral over d omega g equal to 0. So, you see, can integrate this condition. Now, when you have two non-homogeneous terms, you split that solution into two parts, and that is the same thing you do it. Now, let us understand that if you are looking for a solution u in h1 of omega and you are u restricted to the boundary, these are all you have seen it is in h half and of d omega, but then du by d nu is grade du by d nu restricted to the boundary is nothing but grade u. That reduces one more thing, and this has to be interpreted as an h minus half element. You see. So, how do you give an h minus half element, and how do you define that? So, you have du by d nu. If you want to interpret as h minus half, it should act on, because h minus half is the dual of h half. So, you have your duality bracket, and then h half of d omega, this is in d omega as your extensions possible. So, you define this something like integral of grade u, grade v plus integral of, from the equation f v over omega. So, you can do that way. So, with that interpretations, what you have to do is that, so if g is in, if you have g in h half, so you choose u bar. So, this is the way you do it. So, these are all some exercises you have to work it out into looking into various details. So, you have to choose u bar in h1. Of course, if g is in h half, it is better. If start with a g in h half, it would be better. So, you can choose this h1 of omega u du bar by d nu equal to g first, and then look for a solution. Then these are same steps you have to follow. Look for a solution. Every time you look for, it's meaningful. U is of the form u bar plus v, and that will imply your minus Laplacian of v is equal to f plus Laplacian of u bar. Now, you see, and this is on the right side, and you may have to treat it as a L2 or h minus 1 function. That is the way you have to do that one. Okay. And then of course, in that case your problem is dv by d nu equal to 0 on d omega. You can get the all estimates here, and then this will have a solution. The same condition will have a solution if and only if this one f plus Laplacian of u bar 1 equal to 0. That is a compatibility condition. That is equivalent to saying that integral of f with a smooth assumption d omega omega integral of f over omega plus integral over g d omega is equal to 0. So, you can deal with your non-homogeneous situations clearly. So, now let me make remarks. I thought I will cover little more, but then let me make a couple of remarks. I think one, see the Dirichlet condition. Dirichlet condition is specified on the space. Is specified on the space. This is an imposed boundary space h1 naught. So, your boundary conditions are given in the space. So, you need not have to recover it. So, this is called the essential boundary condition. Essential boundary condition. On the other hand, Neumann, the condition, the boundary condition is not there in the space. Boundary condition is not imposed on h1 of omega. You see. So, that actually gives us a naturally. So, the boundary condition obtained naturally. So, it is called natural boundary condition. Okay. So, this is the terminology you would be reading while learning these topics. So, let me make these things very clear. You can also use other type of boundary condition, other types of boundary condition, So, these are all exercises, you should work it out. Okay. So, all what I am not covering is not very difficult. If it is difficult, I may not be giving to you, but these are all it is to make your subject very strong. Whatever you learned it, you should work out for these things. For example, you can impose plus some alpha u equal to 0 alpha positive or other thing. These are called Robin boundary condition. Okay. You can also have oblique type boundary condition du by d nu plus alpha 2 du by d tau. That means this is tangential. Boundary condition, oblique boundary conditions. There are other, you can impose whatever you like, oblique boundary condition. Okay. So, work it out, derive weak formulations, Okay. And what else to do here? Some more things I should be. Yeah, one more thing you can work. While using L naught minus di of aij of dj, this operator. So, the boundary condition, the natural boundary condition is, that means Neumann, natural Neumann boundary. This is what the boundary term, you have to see what is the boundary term coming there. Boundary condition is called the co-normal derivative. So, this is you call it A, we call d nu A is equal to aij of x du by dxj nu I. This is called the co-normal derivative. Okay, good. So, now I will stop here and then we will continue with another lecture. Maybe we will do little bit on bilaplacian problems. Thank you.